got two questions for you. Here's question number one.
Are we still doing circular motion? What are we doing?
Yeah, we're actually starting.
I got 2.4.
That's what I had been doing.
Yes.
All right, everyone, here you go. This car has a mass of m. It goes through a loop of radius r. I want to know the normal force at A and the normal force at B and the normal force at C. And I also want to know what's the minimum V, the minimum velocity, so it doesn't, so that it actually makes the loop and no one falls out.
I have a question. I want to be on the top.
And begin. What's that? And I want it, it'll be it'll be solved in symbol form. And don't forget, will the velocity of the car remain constant?
No.
Yes.
The speed.
No, it won't. It's not a Ferris wheel.
You gotta go up.
Now, if it was a Ferris wheel, it would remain constant, right? But it's not a Ferris wheel.
We would all fall out.
All right. And I will be calling people to the board to give their answers, so make sure you work yours, because I'm sure I'll pick someone who hasn't done it.
Are we coming back to single harmonic motion?
Oh yeah, and then we'll do our second problem, which is this.
Wait, Mr.
Look what you did.
Look, we didn't actually do that. Bianca, now I really want you to fall out of there.
She just laughs.
I wouldn't be so silly. She can't actually push me.
Especially with the fair going on right now.
Are you sure? Sure. Let's my good Six Flags.
Isn't that next week's fighting?
The car. Oh gosh, I've never heard of that. What are you talking about?
We're on the car.
No. Ooh, Aisha. Okay,
That's a
I go
restaurant.
there. I go. Thank you for being
Awesome.
That's not hard. Let's see. Hard, but these.
Okay.
I can't even do number one on my board, guys.
Yeah, there you go. There's question two, because somebody asked about simple harmonic
I'm
motion.
gonna step in.
I'll give you a hint on the first one. Circular motion.
Really?
Really?
So, did you
In
draw?
case you weren't aware of that, because of the big circle on the board.
Oh, wow.
Because of the, the changing of direction thing going on. So will there be acceleration? Yes. Are you looking for a force? Yes. So therefore, we're going to be using free body diagrams and F equals ma, right? Excellent. I'm glad I could be of such help. Minimum velocity at top. I would think it's because they will want to fall out, right? You draw your free body diagram, write your F equals ma. Okay. And it's going to fall out when the top stops pushing on it, right?
Or the normal force gets larger.
So the normal force is zero.
Wait. If n a is
Maybe it doesn't
n
start
squared over r,
And then you have to work
wouldn't that be the
backwards by
same for
energy to find your minimum
c?
velocity to start with.
If that's in a and z plus n squared over r, wouldn't that be the same for c?
Good, don't do it.
I feel like there should be a lot.
Because triple acceleration is v squared over r.
Yes, it is. Okay. Wait.
I think that
First one up here. normal force in each one of these locations, and minimum velocity. So let's look at point A.
I'll do an 8.
You want to do A?
No.
All right, come on.
She
No,
won't.
wait a minute. No, I don't trust you.
Your birthday.
It's her birthday, Andy A. I'll have it.
Andy, can you really do it?
Yeah.
Are you just joking me?
I think it's
All right, here. You ready? Catch. You're going to hit her right in the head. She doesn't even have her hand up. Okay, you ready?
Do it.
I saved you, Superman.
Why do you always miss her?
I'm waiting until she's not looking. Oh! All right, Alex, you're doing B.
I'll do, no, I'll do.
You want to do C? You want to do C? All right. All right, who wants to do B?
I'll do B.
You want to do min velocity?
I could try.
All right. You want to do C? All right, come on up.
I love G as answer.
Wait, no. I don't want to do it anymore.
Don't erase. Don't write over this.
Isn't that ironic?
You're right above or to the right? You're right up here. I know you're height challenged like me. Hard to reach that high.
Don't you race with your jacket.
I know by the time we get
How about y'all switch since you taller?
Chocolate, beef.
I love all the different answers we have here.
You're wrong.
You're subbing for Cindy?
Yeah.
Cindy, you're subcontracting your work?
Does this give you an idea of what happens outside the classroom?
MV squared.
MV squared. What?
I'm starting to turn.
Cindy and Mark switched bodies. That's what happened.
Dad was my classmate.
I know that. And Jake Wooden. Dude, you're horrible.
You gotta be hip with the pin.
I think I'm right with you.
Where's the knee, dude? Where's the knee?
I agree with Mark.
Someone's getting it for I am. I'm forgetting my grammar.
Yeah, when you get married.
It's turning.
It's okay. At least I didn't forget your Spanish grammar.
Mr. Bruin.
That's like
Get that from
I forgot my French grammar.
Got all the alphabet.
no.
It kind of depends.
No, from there you can just use the final answer. All right, Andy. No.
What?
I hate
What do you want?
to tell you you're wrong on your birthday.
Well, if like you have this,
Right now?
I will. I just don't have.
totally flat. Like this is a
She doesn't
circle.
have a shirt.
You're changing direction.
Tal vez cuando no ponemos de más que
But right here, see, it's flat.
No, I drew it specifically on this little curve.
Third spot.
Is it a B or a U?
It's your mother.
Why is it 5?
All right, here we go. All right, let's take a look at normal force
Is
today.
it a B or a U like I said?
You got it? I actually don't know the answer. I just made it up. So we'll find out. All right, here we go, everybody. At point A. At point A, we're in the circle. We're beginning our turn. So if we're beginning our turn right here, we have two forces. We have mg down and we have normal force up. And our normal force up has to counteract mg and cause you to turn. So you have normal force up minus mg down equals mv squared over r. So when you move it to the other side, hey, you get Andy's answer. Okay? What?
I didn't
Hey, you
see
get
it.
Andy's answer. All right, B. Okay, at point B, you have mg down and you have normal force this way. And since your normal force is the only force causing you to go in a circle, your normal force at B equals mac, which is mv squared over r, and you're done.
Fantastic.
Okay,
I don't
at
do
point
that.
C, you have an mg down and you have a normal force down. And so you have normal force plus mg equals mac, which, here we go. There you go, there's your normal force.
Hey, I got it.
Okay? Now, there is one thing that we missed that they will probably add to this type of problem, Now, if this was a if this was a Ferris wheel type problem where the car would always be going the same speed all the way around, then this velocity here and here and here would be identically the same in each case, right? But if this is a roller coaster car, is the velocity here, here, and here in A, B, and C the same?
No.
Oh, how do we find those? What's the easiest way to find them? Probably with conservation of energy. Kinematics technically is not an adequate way to solve this, although when there's no friction, kinematics will give you the same answer, but you won't be given credit because that's philosophically wrong. Because kinematics requires the acceleration to remain constant. And will the acceleration of the car remain constant all the way around? No, it won't. Okay? So you'll be making a bad assumption, which mathematically will get you the right answer, but will get you no points. Okay? It's like one of those happy coincidences where you guess wrong, but you get the right answer. They'll be on to that, and they won't give you any points. So how do we find the velocities? Well, kinetic energy here equals kinetic plus potential at these locations, right? So this is what we would use, conservation of energy, E1 equals E2, to find the velocity at any one of these spots, right? Okay. My last question was, what is the minimum speed so that it makes it through the top? Now, I wasn't really specific about, did I mean minimum speed here or did I mean minimum speed here? So let's solve it for here first, and then we'll work backwards to find the minimum speed required here so that you end up here not falling out. Okay? Because you're going to slow down. Okay. Let me solve it, and we'll see if it ends up the same as Kenneth. All right, at the top, you have normal plus mg equals mv squared over r. That's our sum of the forces equals ma in the downward direction. So we've got, okay, when we're at our minimum speed, the velocity, first of all, does everybody see that what's going to happen is as our car wants to go in this trajectory, parabolic trajectory, but the rails on the roller coaster cause it to go in a circle, right? It will fall out when this trajectory here is less. When the parabolic trajectory is smaller, that radius at the top of the parabola is smaller than the radius of our roller coaster. Does that make sense? So philosophically, you can think of it this way. Whenever the centripetal acceleration down is less than g, then it will fall out. Does that make sense? Or when it's at the same value as g is right when they have the same exact arc at the top. So philosophically, you can do that argument. So when that down equals g down, then you're at your minimum speed. Or you can solve it this way. When you slow down, this side of the equation on the right gets smaller. What on the left side can get smaller? Normal, not mg, because you're not going to change the planet just because you slow down, right?
You could try.
You could try, but it's a futile attempt. How low can normal force go? 0. When that goes to 0, this is minimum. So you get mg equals mv squared over r, and you get the same thing as you get up here. G equals centripetal acceleration. So your minimum speed is g times r square root. Okay? Yes. Here we go. Here's our minimum speed at the top. Kenneth, what did you get? Is that what you got?
That's the minimum speed at the beginning.
Yes, that's the minimum speed up here.
No, it's not.
Yeah, but what I saw for was the minimum speed at the beginning.
Yes, so let's go back here. All right, now, this is the minimum speed when you're at the top. So what would be the minimum speed back here then? All right, so here we go. When you're at the top of the circle, you have velocity and you have height. And your height is equal to 2r, correct? When you go back all the way over here, you have only velocity, right? So let's solve this with conservation of energy to work backwards to find our beginning velocity. So kinetic energy at the beginning equals kinetic plus potential at the top. This is at the beginning, B. Or here I'll put 0 for naught. This is 1/2 mv naught squared equals 1/2 mv at the top plus mgh. Now, these values we know. First of all, we can get rid of m.
B
Yes.
squared.
Oh, v squared, thank you. All right. 1/2, this v squared at the top is going to be g times r, right? By the way, that should be big R. That's my mistake. I listed that as big R up here. So that will be gr plus g times 2r. And I get 1/2 v naught squared. So that would be, all right, I'm going to multiply both sides by 2.
GR plus.
And I get gr plus 4 gr. So I get gr times 5 v naught square root. There we go. Hey, very nice. Good job. Okay, so the minimum speed to begin this whole adventure would be that speed.
That's an adventure.
If you don't start your adventure with that speed, then it becomes a dangerous adventure and you fall out of the loop. Or,
Just go back down.
there are plenty of roller coaster cars that don't start with a maximum speed that's necessary or a minimum speed that's necessary to make it through the loop.
Like Mr. Freeze.
How do they design those roller coasters so they can still go through the loop?
They shoot you off.
They go really high.
They speed up while they go.
Now, you know these roller coasters
Or
because
they go up to a hill.
what kind of restraint do they have?
Oh, they're
They have, instead of this kind,
Like Batman.
they have this kind.
Like Batman.
Yes. Well, like Mr. Freeze, like the flashback, do they still have flashback?
Oh, I
Yeah.
hate that
Yeah, flashback. And
Mr. Freeze
Batman.
had a lap bar.
it doesn't have this over the top?
They got
Yes.
now it's just got-
Oh, it's just a lap bar. So they shoot you up high
It's
enough.
like a weighted one, so it's like sitting on top of you.
Okay.
Yeah, I go to the restroom.
Um,
That ride.
Which ride?
Yeah.
Any ride.
Now,
I love
everybody,
it.
the flashback at Six Flags.
Yeah.
The flashback just has a regular lap harness. They go through that double loop fast enough that there's no way you can fall out. Now, the flashback, on the other hand,
Wait, what?
you...
The shockwave.
Oh, no. The Shockwave, the double loop one.
Okay.
The one right off of I-30.
Right.
Yeah.
Okay.
Oh, that one's fun.
That one's a nice, easy ride. It's fun. They have just a lap harness. There's no way you're falling out of that one. The flashback, on the other hand, you feel that. You feel yourself falling onto your shoulder harness. When you,
It's the one that goes forward
That's
and
right.
backwards.
yeah, it goes forwards through a couple
Yeah.
loops, and then it goes up, and then it brings you back up and goes through backwards.
Oh.
Especially when you go through backwards, you really feel how you're hanging on that shoulder harness.
That's why I don't like it.
Yeah. Dudes, if you ever get on one of those roller coasters and the shoulder harness thing doesn't latch, don't get on.
Why?
The thing is,
Okay, they have those for a reason.
Like when you wrote it, when you went to that place one time, and that guy,
yeah,
Yes. Yeah.
that's how you sit next to a good person.
Yeah, I was in line for the Batman several years ago, and they had a large gentleman get in, and he couldn't make it latch. It came down and went, and it wasn't latching, so he just took that little safety strap and clicked it on. Dude, no way.
Wait, what happened?
especially with like a big
The shoulder harness comes down like this, and then it goes like click, 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 click. He couldn't get it to the first click, because he was a really big guy. And so they have a strap that you can latch onto it, like a little safety strap. And that was all he had on there. And I'm like, don't do it, don't
What?
do
Did he
it.
do it? No.
No, the workers came up and they caught it, that he didn't have it latched. And so they were pushing on it, and they got it to go click, one click. And I'm like,
Poor guy.
yeah, if it didn't click,
wanna ride
you don't,
that
if that doesn't
bad,
click,
you're
don't
gonna
get
miss
on. Yes.
They had an incident at a roller coaster where someone didn't latch it, fell out, so now they're installing a safety switch.
Oh, so that if it doesn't latch, it
At least
can't
the
go?
first latch it sets off an alarm.
Exactly right. Because that little safety harness thing, That, yeah, they're supposed to come by and check. But you know, you come by and check real quick, you're a minimum paid employee.
Yeah, they do.
It's hot, it's in the middle of the day, and you yank on that thing and just the safety latch, safety straps hooked on, you might feel that and think it's latched, but that won't be enough. If you're going around a turn with that much mass, that's not going to save you.
All the way down.
Okay? All
A
right.
little parabolic. My cousin.
Okay.
I
Yes.
love it. The big one.
Yes.
My cousin ended up doing 10.
The death seat. They have a little skull and crossbones, a little tombstone.
And no harness.
All right. No harness. Okay, everybody. Questions on this?
Don't
All right.
erase it. Yeah, please don't erase it.
Circular motion problems. Please go through that review packet I gave you. Make sure you understand the 3 major types of circular motion problems. Remember, every time you have something that changes direction, every time something changes direction, there is a centripetal acceleration. Therefore, there is some combination of forces that causes it to go in a circle, called a centripetal force. All right? One quick thing. The flashback. Next time you drive past the flashback or you're at the Six Flags, look at the loop. The loop looks like this. Okay? Now they're designed that way on purpose because the original roller coaster loops went like this. They were circles. Sort of. They were circles. Okay, now here's the deal. You go slower at the top, you go faster at the bottom, right? So when you need extra speed at the top, you're going slower because gravity's slowing you down, right? So they had to shoot these people into these loops really fast. The problem is that you get almost 0 G's at the top. If you're right at this speed at the top, you get 0 G's. So they shoot you faster through than this at the top, for safety's sake. Okay? So when you come down here, you're speeding up and you would get a much higher velocity, and you would get, in theory, you would get 0 G's at the top and like 2 G's at the bottom, but you're going to get faster than that because you're speeding up, so you get more than 2 G's at the bottom. And they were having people get off these things with like neck injuries because they were going so fast at the bottom. Okay? So how do they cure that problem? Here's how they cure that problem. Look what they do. At the top, notice the radius at the top is this size. Notice what happens. If the radius at the top gets smaller, what's required for minimum speed? Smaller minimum speed required to make it through the loop. Also, look at the radius at the bottom. The radius at the bottom is much larger. That means if the radius at the bottom is larger, let's see, I erased it, but at the bottom you have normal force minus mg equals mv squared over r, or normal force equals mg plus v squared over r. Look, everybody, if this radius at the bottom is small, that increases your acceleration at the bottom, which increases their normal force on you, which increases your g-force. Okay? So how do they eliminate the extra g-forces at the bottom? They make the radius at the bottom larger, which makes this number here smaller, which makes the normal force on your body smaller. So what happens is they can shoot you through slower. They still get enough acceleration at the top so you don't fall out. And they decrease the g-force at the bottom by eliminating or decreasing the velocity at the bottom and increasing the radius. So that's why they make those loops. If you ever go through a roller coaster that has a circular loop, you will feel much greater forces at the bottom than in a loop like this. Okay? You'll experience that. If you've never done this on a loop roller coaster where you lift your hands up, you know, and then you're going through the bottom and you're going, oh. Or you've gotten your head in the wrong spot. Your head's like this and you can't lift it up. You feel like a baby with a 2-ton head, right? Let's talk a little bit about simple harmonic motion and springs and how that adds to our repertoire.
I love the physics.
Okay, all, listen. Simple harmonic motion. Okay, remember this diagram from last year. The magical diagram of all knowledge for simple harmonic motion. Yes, because of you.
It's your fault.
We have to do it eventually.
I like that. It's your fault.
So I can start a new page of notes since it's
We're just adding more, yeah. Okay, here we go, everybody. All right. If this is position A, B, C, D, and E, all right?
Where's Q?
It'll come up eventually as it keeps oscillating. First of all, remember for a spring, negative Kx. Okay, remember the negative just means it's in the opposite direction of x. So if we call to the right positive, and we call to the left negative, then as we stretch this spring out this way, then the spring force will be backwards, okay? In the opposite direction of displacement. Now, just be careful. If they ask the question, what force is necessary to stretch the spring a certain distance, then the negative sign goes away because you're the applier of the force opposing the spring force, right? Just be careful of how it's worded, whether you should put the negative or not in there. Okay. All right. Label on here, everybody, please, where you have maximum force and where force is 0. Here we go. Quiet. Come on. Quiet down. All right. Force max here, but it's a negative force max. Positive force max here, and then everywhere in the center, the force is 0. Okay? Now, label every spot where the acceleration is 0 and where acceleration is maximum, and also state the direction.
Wait, what? They're like,
Label acceleration max and
maximum and then.
Where is the acceleration 0? Where? Where?
force equals 0.
Where force is 0. Because F equals ma. F equals ma. Where the force is 0, the acceleration will be 0. So you have acceleration equals 0 here, here, and here, and you have a negative acceleration max here, and a positive acceleration max here. Okay? Now, because this is true, we can write this equation right here. Since the only force acting on it when it goes back and forth horizontally, then you can say spring force equals ma. And spring force is negative kx, that equals ma. So the acceleration is equal to negative k over m times x. There's our acceleration in simple harmonic motion as long as it's horizontal. Okay? Yes.
vertical involves.
Now vertical, we'll talk vertical later. We're just talking some basic stuff here. All right, what about displacement? Does everybody see that displacement max is over here? Displacement minimum is over here, or maximum negative is over here. Okay? Okay, what about velocity? Where's our velocity max?
At the center, or where x is 0.
Okay, velocity is 0 here, velocity is 0 here. Velocity is max, but right here, is it positive or negative max?
Positive.
Positive velocity max, negative velocity max, positive velocity max. Okay? All right. Now, what about potentials and kinetic energies?
Well,
Oh my
we have
God.
a Vmax.
All right. Since this is related to kinetic, this is kinetic max. Is it positive or negative kinetic max?
Scalar.
So it's positive. And so this would be positive kinetic max. And this would be positive kinetic max because it's a scalar. Because kinetic energy is 1/2 mv squared, right? And so velocity positive or negative, you're going to get positive kinetic. Kinetic energy is 0 on the ends. Okay, what about potential energy?
1/2 km.
Okay, wherever X is maximum, you get maximum spring potential energy. But again, since spring potential energy is 1/2 kx squared, since x is squared, this will always be positive, okay? And we get 0 in the middle. All right, so let's look at this from energy standpoint. Kinetic energy maximum at the end will equal spring potential maximum at the center. So 1/2 kx squared equals 1/2 mv squared. I swapped them, sorry. My halves go away, and I get velocity maximum equals k over mx square root, right? Notice we get this k over m again. All right? Spring constant over mass. All right, you got to be able to derive this. You got to be able to derive this. Not a big deal. Okay, so now let's look at the graphs real quick. Displacement versus time. If displacement versus time looks like that, what does velocity versus time look like?
Well, let's call that displacement.
Hey, if we call this cosine,
Oh, now we're going to call it sine.
I'm sorry, if we call this sine, don't call it cosine, you messed me up. If we call this sine, and we take the derivative of that, because that's a velocity, then what do we get? Cosine or negative cosine? Cosine. So we start here, end here,
Positive.
like that, right? So there's our velocity. What's our acceleration look like?
Negative sine.
Ah, it's going to be the derivative of the velocity, which will be a negative sign. So it looks like this. And there's your acceleration. Hey, this is the nice thing about having students that have had calculus, because that's so much easier to explain.
And then if you graph the haircut,
If you graph the jerk, then that would be negative cosine. But we don't go that far.
why not?
Because we don't.
But it would be jerking.
Yes, but we
Do
don't.
you know how to jerk? No, I can't.
Okay, graph energy versus displacement.
Total energy.
All right, what's total energy look like?
It's a flat line.
Total. What does potential look like?
Well, let's say negative x. It's
That one's easy, right? Hey, I'm losing some of you. Boys in the back, stop. Potential energy. What's the graph like? All right, we're going to have a new seating arrangement next time. You two will be up front. We'll bring 2 chairs up, and you can be right up here. And you can carry on your conversations about physics right here.
Is it spring potential or gravity?
Spring potential energy. We're talking this one. Now, it keeps going, but if we only have total energy there, it looks like that. And then kinetic will look like that.